Hi, I am Hemang Chawla and I'm pleased to present our work, Adversarial Attacks on Monocular Pose Estimation, along with Arnav Verma, Ilahi Arani, and Behram Zonos. Vision systems have benefited immensely from the progress in deep neural networks, enabling a wide variety of scene understanding tasks. Two of the prominent tasks in 3D scene understanding for robotics and advanced driver-assistance systems are monocular depth and pose estimation, often learned together in an unsupervised manner. The depth network takes a single image as input and outputs pixel-wise depth. The pose network takes a pair of consecutive images as input to output their relative rotation and translation. Nonetheless, while deep neural networks have achieved state-of-the-art performance in several perception tasks, they remain vulnerable to adversarial attacks that fool the network with often imperceptible changes to the input. This limits their applicability in safety-critical tasks where the margin for error is low. Recent works focused on vulnerability of monocular depth estimation, demonstrating untargeted and targeted attacks on the predictions. Observe how the predictions can be flipped horizontally or vertically. Works have also compared transformer-based methods to convolutional neural networks, showing how transformers make the networks more robust. However, none of the existing works focus on adversarial attacks for monocular pose estimation. We demonstrate adversarial attacks on monocular pose estimation using state-of-the-art SC depth method as an example. The objective is to find a perturbation C as a function of the input image pair X such that an incorrect pose is predicted for the generated adversarial example. This is achieved by maximizing an adversarial loss function iteratively. To keep the adversarial changes imperceptible, the perturbation is bound by the attack strength epsilon and the pixel values are kept in valid range. We study adversarial attacks on monocular pose estimation through different questions. First, are pose estimation networks vulnerable to untargeted adversarial perturbations designed to cause mispredictions? For untargeted attacks, we use the training target as the adversarial loss. We observe that pose estimation networks are vulnerable to untargeted adversarial perturbations. The relative pose errors increase with the attack strength, reaching up to 3 times the error for the clean input. Next, we study if pose estimation is vulnerable to targeted adversarial perturbations designed to cause specific mispredictions, such as an incorrect direction of translation or rotation. We propose 3 kinds of targeted attacks on the yaw, on the translation, and on the complete pose. We observe that the targeted attacks lead to notable errors in the predictions that are more severe than for the untargeted attacks. These attacks not only increase the trajectory drift, but also alters its geometry. Next, we also study if the targeted attacks on translation impact the output rotation and vice versa. We find that indeed, the features learned by the pose network relate rotation and translation with each other. Hence, attacking translation results in degradation of predicted rotation and vice versa. For example, the targeted attack on yaw at attack strength 4 increases the RPE degrees by 18 times for sequence 9, while also increasing the RPE meters by nearly 5 times. Since the depth and pose estimation networks are trained simultaneously, we also examine if the adversarial images generated to fool pose estimation networks also fool the depth estimation networks and vice versa. We find that the networks are not vulnerable to such cross-task attacks. Adversarial perturbations generated to attack depth and pose estimation networks are different, and the images generated to fool the depth or pose network do not impact the other. Finally, we examine the transferability of the pose adversarial perturbations to other methods. It allows us to study if access to a specific pose estimation model allows generation of adversarial images that can attack other networks to which we don't have access. By utilizing the adversarial images generated from SC depth, we attempt to attack two different methods with different losses and architectures, namely G2S and MTSFM learner. We utilize G2S, which uses a similar CNN-based architecture as SC-depth. However, it uses slightly different set of training losses. Next, we utilize MTSFM Learner, which uses a transformer-based architecture, unlike the CNN-based SC-depth. We observe that untargeted adversarial perturbations do not transfer to other models. However, targeted adversarial perturbations do transfer to the other models with different architectures and training losses. They result in an increased odometry drift, but do not catastrophically alter the shape of the trajectories. In summary, we find that pose estimation networks are vulnerable to the proposed untargeted and targeted attacks. The targeted attacks are stronger and affect not only the trajectory drift, but also its shape. Attacking translation impacts the rotation and vice versa, but the type of perturbations that attack pose are different from those that attack depth, limiting cross-task attacks. Finally, we find that pose adversarial attacks are transferable to other networks with different architectures and training losses. Thus, reliable deployment of pose estimation models still remains a concern. Thank you.